If, like me, you grew up somewhere with a questionable education system, chances are your exposure to music theory was limited. Maybe you were just handed a recorder and a half hearted diagram of the treble clef, and that was supposed to be enough. Maybe it never made any sense. Maybe it still doesn't. Over time, I started piecing things together on my own. And looking back, I keep thinking there are ways this could have been explained to me that would have actually made more sense. Ways that are connected to the things we already understand. In this video, I want to share some of that, not to teach music theory in the traditional sense, but to show how ideas like harmony, contrast, and structure exist across different senses, starting with something visual. Color theory gives us a language to talk about relationships, about tension and resolution, about dominant tones, contrast, gradients, ideas that also exist in sound, from the color wheel to the circle of fifths, from shades to harmonics. There's a structure underneath both that's surprisingly familiar. So let's start there. Color theory begins with the wheel, a circle that arranges colors in a way that mirrors the visible spectrum. Red flows into orange, orange into yellow, and so on. A smooth, continuous gradient. But once it's looped into a circle, patterns emerge. Some colors sit comfortably next to each other, others pull against each other. Some combinations feel gentle, others feel loud. Analogous colors are close together on the wheel. They blend easily. Think blue, teal, green. Used together, they create coherence, not much friction, just flow. It's like languages with a shared roots. Spanish and Portuguese, for example. Different, but with enough overlap to feel familiar. One bleeds into the other. You can move between them without too much resistance. Complementary colors, on the other hand, sit opposite to each other. Blue and orange, red and green. These combinations create tension, not because they're wrong, but because they highlight each other's differences. They create contrast. They demand attention. This is less like Spanish and Portuguese and more like Spanish and Japanese. The structure, the rhythm, the very foundation of the language is different. That clash can be beautiful, but it's unmistakably a clash. Then there's dominance. Most effective color palettes have a single dominant hue, the main color that sets the tone, and a few accent colors that support or contrast it. Not everything can speak at once. Dominance brings focus. It decides what the viewer notices first. We can break color down into its three fundamental components: hue, saturation, and luminosity. Hue is what we usually mean by color. It tells us where a color sits on the spectrum. Saturation is how pure or intense the color is. Highly saturated colors are vivid and bold. Low saturation means muted, washed out, or closer to gray. Luminosity, or brightness, is how light or dark the color appears. Think of it as how much white or black is mixed into it. If you imagine a single hue as a word, then saturation and luminosity are the tone of voice and volume. You can say the same thing loudly or softly, brightly or darkly. The meaning shifts even if the content stays the same. All of this exists in sound. In music theory, there's a diagram called the circle of fifths. At first glance, it looks a lot like the color wheel, but instead of colors, it's made of musical notes and keys. Let's pause there for a second. What's the difference between a note and a key? A note is a single sound like C, G sharp, or F. It's a pitch, a point in the frequency spectrum. A key, on the other hand, is a collection of notes. It's a tonal framework that defines a central pitch, referred to as a tonic, and a set of related notes known as the scale, around which melodies and harmonies can be organized. Together, they create a tonal center and a context. Western music divides the octave into 12 pitch classes. These are the 12 unique notes that repeat across the octave. The circle of fifths arranges them in a very specific order. Each step moves up by an interval of a fifth. That means the closest point to any given note in this system is the note that's 5 scale degrees above. Starting at C, you move to G, then to D, then to A, and so on. The closest two tones are in the circle of fifths correlates with the number of shared diatonic pitch classes between them, meaning that the closer two tones are, the more they have in common. Think of it this way. C is to G what Spanish is to Portuguese, or what red is to orange. Different, but closely related. If you're interested in non-Western approaches to pitch and tuning, I've made a separate video explaining the basics of Hindustani classical music. You can click here, and I'll also leave a link in the description. The circle of fifths is organized in this way because it's the most stable consonant interval after the octave. When you play two notes a fifth apart, their harmonic overtones align closely. They reinforce each other. The sound feels open, balanced, natural. It also turns out that stacking perfect fifths is a systematic way to move through all 12 notes without repeating until you complete the cycle. If you go up by a fifth 12 times, you land right back where you started, only several octaves higher. It's a closed loop, a map of relationships. I would recommend spending some time playing with and moving around these symbols. What you're really training here is pattern recognition, the ability to see structure emerge through repetition and transformation. This is something musicians are especially good at. Take a simple example, the 2-5-1 progression, arguably the most widely used pattern in jazz. If you write down every pitch following the circle of fifths and systematically apply the 2-5-1 logic, you'll start to see these patterns appear. And just like in chess, once you begin shifting pieces around, new configurations emerge. These patterns help you internalize intervals, functional relationships, and harmonic motion, not as isolated facts, but as relational systems. Like the color wheel, proximity matters. Notes or keys that are next to each other on the circle are closely related. They share many common tones. But if you move across the circle, things change. The key on the opposite side of another key shares almost nothing. The concept of contrasting music appears as dissonance. The maximum tonal distance between two keys is said to be a tritone away. If you play C and F sharp together, it's tense and unresolved. It's like jumping from red to green. Not subtle, not smooth, but very effective when used with intention. Because it splits the octave cleanly in half. It spans 3 whole tones, hence the name, and lands in a space that doesn't quite feel at rest. It resists resolution. It creates tension by design. For a long time, there's been a myth that this interval was banned in medieval Europe because people believed it could summon the devil or something, but that's not true.
This interval was called the Diabolus in Musica, which
So there was
means
this
the devil
chord that
in
was banned in the
music.
Middle
It's
Ages by the
back in the
Catholic
old
Church
days,
because they thought it sounded
signified
demonic and
excommunicate.
devil was
There is no hard evidence suggesting that it was banned. It was just avoided sometimes because it was hard to sing to and sounded jarring to the ears at the time. The phrase Diabolus in Musica, or the devil in the music, came along much later, as a colorful nickname, not a church decree. If you're curious to dive deeper into this history, I highly recommend Adam Neely's video on the topic. He breaks it down in great detail. Fun fact about the tritone though, it later became a cornerstone of heavy metal. The first notes of the first song on Black Sabbath's first album are trichomes. It doesn't get more on the nose than that. Black Sabbath is widely credited with inventing metal, so in a way, the entire genre began with the idea of the devil in the music. I don't know, maybe that's what gave them their edge.
Are you sober now?
No, yeah,
Yeah.
I'm never, but I'm going to.
To sum up, the circle of fifths is like a map of musical harmony. Sections near each other are consonants, compatible like analogous colors, and sections across the circle are dissonants, clashing like complementary colors. We even have a notion of dominant tones guiding the ear home. Just as a dominant color guides the eye, the geometry of music and visual art line up neatly. No wonder why some people experience synesthesia and literally see colors when they hear certain notes or chords. The patterns of one often echo in the other. Now that we've drawn parallels between color and music through these circles, let's talk about how we navigate them. In visual arts, we have coordinate systems for color, like RGB or CMY values. In music, we have notation and terminology to pinpoint any sound's position in the spectrum of audible frequencies. Pitch is the word we use to indicate where a note lies on the spectrum. When you look at a piece of sheet music, you're basically looking at a map of sound frequencies. Each note on the staff is like a coordinate on a map, pinpointing a particular pitch in the spectrum of sound. A4, for instance, corresponds to 440 hertz in frequency. That's its address in the sound spectrum. If you play any sound at that frequency, say a flute, a piano, or even if you whistle at that exact tone, you have successfully found A4 on the map. If you go up one octave to A5, that note vibrates at 880 hertz, exactly double the frequency. Go to A6, it's 1760 hertz, and so on. Yes, A4 at 440 hertz is not a universal law of nature. It's just a convention. Different periods, cultures, and ensembles have tuned at higher or lower frequencies, sometimes quite significantly. In the 19th century, orchestras often tuned closer to 435 hertz. Some modern ensembles and recordings use 432 hertz, for example. Others go higher depending on historical practice or stylistic preferences. But for the purpose of this video, 440 hertz functions as a shared reference point, a standardized coordinate system that lets us talk clearly about pitch, frequency, and musical relationships. Every musical pitch can be given a number, and its frequency can be measured, usually in hertz. And those numbers map out a spectrum. Even non-musical sounds, like a bird chirping or a car honking, contain frequency components. When one of those components is strong enough, we perceive it as pitch. If that dominant frequency roughly lines up with one of these note addresses, you can place the sound on the map. For example, the hum of a vacuum cleaner doesn't produce a single note. It produces a bunch of frequencies. But if its strongest partial sits around, say, 300 hertz, we tend to hear it as something close to D sharp on the piano, even though the sound itself is noisy and unstable. If a bird sings around 3000 Hz, we would perceive it as being somewhere between B7 and B6. We don't think of these as music, but they still occupy positions on the spectrum. This shows that the map of notes is just a convenient reference for all possible sounds, not only for those we consider music.
I crisscross applesauce and oh my god. Oh my god, oh my god. Oh, it just keeps getting better. Oh! Rookie 7 is next and then bishop f5. Give me the f***ing queen. Oh! Yes! Yes! Oh, we're taking everything.
If pitch tells us what a sound is, rhythm tells us when. And just like pitch, rhythm gets mapped. In standard music notation, we use notes, and each note has a temporal value, a duration. Time itself is divided into chunks we call bars or measures. Each bar follows a time signature. This is basically the music's grid system. It tells you how much time you have to work with and what unit you're measuring it in. Take 6/8 time, for example. The top number tells you there are 6 beats in each bar. The bottom number tells you that an eighth note is 1 beat. So 6/8 note beats per measure. That's your grid. But just because it says 6/8, it doesn't mean you have to only use 6/8 notes. You can divide the time however you want. Dotted quarters, triplets, syncopations, rests, whatever fits. Think of it like Sudoku. Every square has to be filled, only in here, there's more than one way to do it. Even silence counts. There are also conventions around which time signatures you use and why. Even if multiple signatures could technically fit the same number of notes, they don't feel the same. A piece in 6/8 flows differently than one in 3/4, even though both add up to 6/8 notes. One might swing, the other might march. Composers choose time signatures not just for mathematical reasons, but for feel. To shape how the music moves, breathes, and grooves. Note values are relative. A whole note is twice as long as a half note. A half note is twice as long as a quarter note, and so on. Each note also has a rest, a silent version of the same length. So a quarter rest holds the same space of a quarter note. A whole rest holds the same space of a whole note. It's the same grid space, just empty. This is what gives music its structure and its breadth. It's not just about what you play, but also about what you don't play. Rests are negative space. They create tension, pause, and shape. They make rhythm feel alive instead of mechanical. Zoom out, and you're really just moving blocks around inside a box. Sound and silence arranged in time, like puzzle pieces that only work when they add up. Every sound you hear, musical or not, isn't made of a single pure tone. It's actually a blend of many frequencies layered together. There's usually one main frequency that defines the pitch we hear. That's called the fundamental. You can think of it like the hue in color, the dominant ingredient that gives the sound its identity. But sitting above are other frequencies, usually quieter, called overtones or harmonics. These are like tints and shades layered over the base color. They don't change the fundamental pitch, but they shape how it feels, whether it's warm, harsh, hollow, or bright. The specific mix of these harmonics is what gives each instrument or voice its own timbre, which fittingly is also known as tone color. Imagine the fundamental as a base color of paint, say a pure blue. Now imagine you mix in a little bit of white or a little bit of red. You'll still see blue, but its character changes. It might become a lighter blue or a purplish blue. Similarly, when an instrument plays a note, we still hear it as that note. but the presence of other faint tones mixed in will make it sound brighter, darker, cold, warm, and so on, depending on which harmonics are strong. A flute playing A4 and a violin playing A4 are playing the same fundamental pitch, yet they sound very different. That's because the flutes and violin generate different harmonic recipes. The flute sound has a relatively strong second harmonic, that is 2 times the fundamental, and not much else layered on top. That's why it sounds so pure and whistle-like. In fact, with flutes, what we often hear most clearly isn't the fundamental at all, but the octave above it. That gives the sound its light, airy feel. A violin, on the other hand, is much richer. When it plays in notes, it doesn't just give you 1 or 2 frequencies, it gives you a whole stack. Twice the base frequency, 3 times, 4 times, 5, and so on. These are called harmonics, and they're all ringing out together, adding complexity and color to the sound. That's part of why a violin feels more textured and expressive than a flute. It's made of more stuff, more moving parts. These harmonics are not just arbitrary. They follow a natural pattern called the harmonic series. If the fundamental is like the root color, the harmonics are like a rainbow of related frequencies that are mathematically related. Our ears tend to like frequencies that line up in simple whole number ratios. These intervals sound smooth or consonant to us because their sound waves reinforce each other in a predictable, regular way. They don't clash, they click. Honestly, it's just how our brains are wired. When waveforms align cleanly, our auditory system has an easier time processing them. It's like the brain goes,
Okay, I guess that makes sense.
you can think of it like color. Just as certain colors blend well because they share components, like how teal and green flow into each other, certain notes blend well because their harmonic structures overlap. If you stack up harmonics in specific ratios, you start getting the raw ingredients of chords and intervals we tend to find beautiful. So, harmony isn't just about notes, it's about how the harmonics inside these notes line up. The simpler the relationship, the more our ears go.
Yes, science!
However, not all sounds are nicely harmonic. Some instruments or sounds produce inharmonic overtones, meaning that their overtones are not neat multiples of the fundamental. For example, percussion instruments like cymbals or drums have lots of frequencies that don't line up in the harmonic series, which is why their notes don't have a clear pitch and sounds more like complex bursts of sound. If pure tones are like pure colors and harmonic tones are like mixed but harmonious colors, then inharmonic sounds are like very complex colors that are harder to identify. Imagine a multicolored texture pattern. Interesting, but you can't really identify a main hue. The key takeaway is every sound has a spectrum of frequencies, and this spectrum is like a recipe that defines the sound's color. Music theory tends to oversimplify this by focusing on the fundamental tones only, but the real thing is much more complex. Understanding fundamentals and harmonics gives us a better sense of why instruments sound the way they do and how they interact when played together. For composers, it adds another layer of thoughts when choosing instruments or sounds for a piece. It's a bit like picking spices when you're cooking. You're not just thinking about how one ingredient tastes on its own, but how it will behave in the context of the whole dish, what flavors will emerge in combination. This is a perfect example of emergence, where the end result is greater than the sum of its parts. You can try a little experiment if you have access to a piano. If you play a low note gently and listen closely, alongside the main pitch, you may notice a faint higher ringing tone. That sound is often the first overtone, the octave above the fundamental. This happens because a vibrating string doesn't move in a single way. It vibrates simultaneously in multiple notes, producing a series of higher frequencies stacked above the main pitch.
The series, according to the laws of physics, has to be exactly an octave higher than the fundamental C we've been hearing. In other words, it's going to be this C, an octave higher. Now, if I silently press down the key of this higher C and hold it so that the string is free to vibrate, and then abruptly strike the fundamental C an octave lower, what do you hear? You are clearly hearing the first overtone vibrating sympathetically an octave above its fundamental. I hope you heard it, did you? Listen again. Clear as a bell.
You can hear this more clearly on a guitar. If you lightly touch a string at its halfway point and pluck it, the fundamental is suppressed and the octave harmonic is isolated. The result is that bell-like harmonic tone, an overtone made audible by controlling how the string is allowed to vibrate. With travel from color to sound, from the canvas to the staff, we saw that the color wheel and the circle of fifths are like siblings. Both are circular maps showing which ingredients mix well and which ones clash. We learned that notation is a map of music, giving each pitch an address in the spectrum. We broke apart sound into fundamentals and harmonics, discovering the secret recipe that gives instruments their unique tone colors. Throughout, an important theme emerged. Theory, whether color theory or music theory, is descriptive, not prescriptive. It's there to explain why some combinations feel harmonious and others contrasting, and to give us a common language to talk about it. But it doesn't create art by itself. An artist can break color rules to create a striking painting. A composer can break musical rules to invent a new sound. And it might still work brilliantly. That's because theory is a map that can show you several paths to drive from point A to point B, but which route you take, or if you forge a new path altogether, is up to you, and each journey can have its own surprises. Always remember that creativity lives in the territory of experience.